Like a riddle, right? Or maybe something straight out of science fiction. But what if I told you this isn't just a thought experiment? It's actually a real-world, kind of mind-bending challenge happening right now at the absolute forefront of physics. We're talking about antimatter.
Exactly. And what's really fascinating, I think, is that antimatter isn't just some theoretical idea floating around. It's real. And the challenge, the huge challenge, is how do you trap it? How do you hold it and study it without it immediately annihilating with ordinary matter? It's one of the most profound scientific and engineering puzzles of our time.
And that's exactly what this deep dive is all about, antimatter containment. It's the incredible science, the engineering involved in literally bottling something that, by all accounts should be impossible to contain.
Right.
It's a fundamental challenge, really pushing the boundaries of how we understand the universe. So our mission today is to give you, our listener, a shortcut to getting up to speed on this pretty complex topic.
Yeah, cut through some of the complexity.
We're going to unpack the core principles, reveal some surprising facts, look at the cutting-edge technologies that make this even possible, and ultimately figure out why this seemingly, arcane research is actually crucial for answering some of the biggest questions in physics.
And you absolutely have to contain it to study it. I mean, that's the baseline. You can't observe something if it just vanishes the second it touches your detector.
Right. No contact allowed.
So containment isn't just a technical hurdle. It's literally what makes the discoveries possible.
I see. Okay, so let's start right at the beginning. What exactly is antimatter?
Well, in essence, antimatter is just matter made up of antiparticles. For almost every fundamental particle we know in ordinary matter, there's a corresponding antiparticle. Think of it like a mirror image.
A mirror image. How so?
They have the exact same mass, but opposite electric charge and some other quantum numbers are flipped too. So the electron, negatively charged. Its antiparticle is the positron, positively charged.
Okay.
A proton has an antiproton, also opposite charge. Even the neutron, which has no net charge, it has an antineutron that's made of antiquarks.
So just like we build atoms from particles, you can build antiatoms from antiparticles, like antihydrogen, a positron orbiting an antiproton.
Precisely.
Does that mean you could theoretically have, an anti-elephant?
Well, in principle, yes. There's a core idea in physics called CPT symmetry. It predicts that particles and their antiparticles should have identical properties, same mass, same decay lifetimes. They should even respond to gravity identically. Just the charges are reversed.
So an anti-elephant would look and act just like a regular elephant, just made of antimatter.
Theoretically, yes. And an anti-star would shine just like a star. And importantly, antimatter should fall downwards under gravity, just like normal matter.
Okay, that's a pretty big prediction from CPT symmetry. Has that actually been tested? I mean, are we sure antimatter falls down? Or is that still theory?
Oh, that's a great question. And actually, yes, it has been tested quite recently. CERN's alpha experiment made a really significant measurement confirming that antihydrogen atoms do fall downwards, just like matter.
Wow, okay.
It was a huge deal. It directly observed it, which helps rule out some of the, let's say, more exotic ideas like simple anti-gravity that you sometimes hear about.
Right, so no anti-gravity. Got it. Now, this next bit is obviously key to the whole containment problem. What happens when matter and antimatter actually meet?
Annihilation, that's its defining feature.
Yeah.
When a particle and its antiparticle collide, they mutually annihilate each other.
Gone.
Completely gone. And the process converts 100% of their combined rest mass into pure energy. It follows Einstein's E-Mass-Seapot perfectly. It is by far the most efficient energy release we know of.
100% conversion. It's way beyond anything else, isn't it?
Oh, absolutely. Compare it to nuclear fission, in power plants. That converts less than 0.1% of the mass into energy. Nuclear fusion, like in the sun, maybe around 0.7%. Antimatter annihilate, it's the whole thing, 100%.
So what kind of energy are we talking about? Give me a sense of scale.
Okay, try this. If you took just 1 gram of antimatter and 1 gram of matter and let them annihilate, boom, you'd release about 1.8 times 10 to the 14 joules.
Which is
a lot. That's equivalent to about 43 kilotons of TNT from just 2 grams of stuff.
43 kilotons, like a nuclear bomb from 2 grams. That's just incredible. And what actually comes out of this explosion? Is it just light?
Well, for the simplest case, electron-positron annihilation, yeah, you mostly get high-energy gamma rays, 2 or sometimes more. But for proton-antiproton annihilation, it's much messier. You get a whole shower of other particles, energetic photons, neutrinos, things called mesons, which decay quickly, Most of the energy comes out as nasty ionizing radiation.
Right, so this huge instantaneous energy release. It makes antimatter sound like this amazing future fuel source for rockets, but also incredibly dangerous.
Exactly. Both are true. It's tantalizing for future applications, maybe deep space propulsion someday, far, far off. But it's also an extreme hazard that demands just unprecedented levels of control.
Which brings us squarely back to containment. If anything made of matter touches it, poof, it's gone. So what are the absolute must-haves for isolating something that's reactive?
Number one, absolute necessity. Non-contact confinement. You just cannot use a physical container. It would instantly react with the walls, so you have to levitate it.
Using what? Magic?
Close. Using electric and magnetic fields. But that's not all. This levitation has to happen inside a near-perfect vacuum. We're talking ultra-high vacuum, UHV.
By the vacuum.
Because even stray gas molecules, just a few random atoms bouncing around, will collide with the antimatter and cause annihilations. That destroys your precious sample bit by bit, and it generates hazardous radiation inside your experiment.
And getting that kind of vacuum must be hard.
Oh, it's a huge technological feat in itself. You can spend months pumping down a chamber to get to UHV, and then one tiny leak, a microscopic pinhole, and poof, your antimatter just winks out of existence. It's this constant battle.
That sounds like a real paradox, though. You need this perfect isolation, sealed off from everything.
Right.
But you also need to study it, right? You need to poke it with lasers or microwaves to measure things. How do you do that if you can't touch it?
You've nailed the core challenge. An antimatter trap isn't just a passive box, like a thermos. It has to be this incredibly controlled environment that does two contradictory things at once. Prevent all the destructive interactions with matter, but allow specific, non-destructive interactions like with laser light so we can actually learn something. It's all about controlled interactive containment.
Okay, so let's get into the nuts and bolts. How do scientists actually levitate these charged antiparticles, the antiprotons and positrons?
Right, before you make antihydrogen, you handle its charged bits. The main tool for this is called the Penning trap. It's basically an electromagnetic bottle, no physical walls.
An electromagnetic bottle. How does that work in 3D? How do you stop them escaping sideways and lengthways?
Okay, it uses two types of fields. For radial confinement stopping particles drifting outwards, you have a really strong, uniform magnetic field running right down the central axis of the trap, usually from a big superconducting solenoid magnet.
Right.
This powerful field forces the charged antiparticles, like antiprotons or positrons, to spiral tightly around the magnetic field lines. It's called cyclotron motion. They're basically locked onto those field lines. They can't easily move outwards.
Okay, so that handles sideways escape. What about along the field lines, out the ends?
For that you use a static electric field, specifically a quadrupole electric field. This is set up by a careful arrangement of ring-shaped electrodes around the central axis. This creates an electrostatic potential, well, basically an electric valley that gently pushes the particles towards the middle of the trap and repels them if they try to drift towards either end.
So magnetic field holds them in, electric field keeps them from shooting out the ends. Clever.
Exactly. Together, they provide stable, three-dimensional trapping without any physical contact.
So that works for trapping, say, one antiproton or a few.
Yeah.
But you mentioned earlier you need billions or trillions to make enough antihydrogen. How do you hold that many?
Yeah, for larger quantities, they use a specialized version called the Penning-Malmberg trap. It's specifically designed to hold huge numbers, billions, even trillions of charged particles of the same type, like all positrons or all antiprotons.
Okay.
This forms what we call a non-neutral plasma. It's basically a cloud of identical charged particles behaving collectively. It's a plasma, but it's not electrically neutral overall because there's no balancing charge.
And these can hold a lot for a long time.
They're remarkably good. They can store these non-neutral plasmas for hours, sometimes even days. There was an experiment at CERN called TRAP. They managed to hold a single antiproton for a world record 57 days.
57 days for one antiproton. That's unbelievable stability.
It really is. Shows you how well these traps can work under the right conditions.
But just holding them isn't enough, is it?
Yeah.
You mentioned they come out hot from the accelerator. You need to prepare them somehow for making antihydrogen.
Precisely. The antiprotons you get from the accelerator are very energetic. They're hot, moving around with a wide range of speeds. To get them to efficiently combine with positrons to make antihydrogen atoms, you need to cool them way down to very low temperatures. And you also need to compress them into a dense cloud so they actually overlap and interact.
Cooling without touching. How's that done?
Well, it depends on the particle. Positrons are light, so they cool down quite easily through something called cyclotron radiation. As they spiral in that strong magnetic field we talked about, they naturally radiate away energy as photons. They basically shed their kinetic energy until they reach the temperature of the trap environment, which is usually kept cryogenically cold, around 4 Kelvin.
Okay, so positrons sort of cool themselves. What about the much heavier antiprotons?
Yeah, antiprotons are almost 2,000 times heavier, so that radiation cooling is much, much less efficient for them. They need help. We use a technique called sympathetic cooling.
Sympathetic cooling.
You take a cloud of electrons, which do cool easily via radiation, and you pre-cool them down to 4 Kelvin. Then you introduce these cold electrons into the trap where the hot antiprotons are. They mix together. Through collisions, the energetic antiprotons transfer their heat energy to the cold electrons. The electrons then efficiently radiate that excess energy away, so the antiprotons cool down by sympathizing with the cold electrons.
Clever. Like dunking a hot potato in cold water, but with plasmas?
That's a decent analogy, yeah.
And then compression. How do you squeeze the plasma cloud tighter?
For that, they often use a technique called the rotating wall. They apply a special kind of rotating asymmetric electric field to the plasma column. This field essentially exerts a torque on the plasma, spinning it up and pushing the charged particles radially inward towards the center.
Oh, okay.
This can significantly increase the density of the plasma, which is absolutely crucial. You need the antiprotons and positrons to be densely packed and overlapping if you want them to actually meet and form antihydrogen.
So the big takeaway here seems to be that these traps aren't just passive containers.
Not at all.
You're actively manipulating these tiny, fragile clouds of antiparticles, cooling them, squeezing them. It sounds less like a bottle and more like a highly controlled chemical reactor or something.
That's a really good way to put it. A quantum-level test tube, maybe. We can precisely tune the conditions, temperature, density, even the shape of the plasma, much like a chemist would optimize conditions for a reaction. That control is key.
Okay, so we've figured out how to trap and prepare the charged building blocks, antiprotons and positrons. But the real prize for many of these experiments is neutral antihydrogen. And you said that's where it gets really tricky.
Yeah, this is the neutrality problem. As soon as an antiproton captures a positron and forms an antihydrogen atom, the whole thing has a net electric charge of 0. It's neutral.
And that means?
It means it completely ignores the electric fields of the Penning trap that were holding the charged particles. An antihydrogen atom formed inside a Penning trap would just drift. It wouldn't feel the electric potential well anymore. It would just float sideways until it hit the trap wall.
And annihilate instantly.
Instantly, in microseconds. So you need a completely different trapping mechanism for neutral antiatoms.
Okay, so if electric fields are out, how on earth do you hold on to a neutral antiatom? What's the handle?
The handle is its magnetic moment. Even though it's electrically neutral overall, the antihydrogen atom still acts like a tiny, tiny bar magnet.
Why?
It's mainly due to the spin of the positron orbiting the antiproton. This gives the atom a net magnetic dipole moment. Now, this magnetic moment doesn't really feel a force in a uniform magnetic field, but it does experience a force if the magnetic field is spatially varying, if it's inhomogeneous, stronger in some places, weaker in others.
Ah, so it's like putting a tiny compass needle in a magnetic field that isn't smooth but lumpy.
Exactly like that. And crucially, some atoms, depending on their quantum state, are low field seeking. They are repelled by regions of strong magnetic field and attracted towards regions where the field is weakest.
Okay.
So if you can engineer a magnetic field configuration that has a definite minimum point, a spot where the field strength is lower than anywhere else around it in all 3 dimensions, then you can trap these low field seeking antiatoms right there in that magnetic dip or well.
And that's the job of the Ioffe-Pritchard trap, right? How does that create this 3D magnetic valley?
Right. The Ioffe-Pritchard trap, or variations of it, uses a combination of magnets. For radial confinement, stopping atoms drifting sideways out of the minimum, it uses what's called a multipole magnet. Modern experiments like ALPHA often use an octupole magnet.
Octupole.
Yeah, based on the 8 magnetic poles arranged around the axis. This creates a magnetic field that is 0 right at the very center on the axis and gets stronger and stronger the further you move away radially. So that forms the bottom of the well sideways.
Okay, that keeps them centered. What about escaping along the axis out the ends of the valley?
For that, you need plugs at the ends. The trap uses 2 strong coils, often called mirror coils, one at each end. These generate regions of high magnetic field strength. When a low field-seeking antiatom drifting along the axis encounters this strong field, it gets reflected back towards the center, like hitting a magnetic mirror.
So multipole magnet for the sides, mirror coils for the ends, creates a 3D magnetic bottle minimum.
Exactly. That combination creates the 3D magnetic well. But the key thing to realize here is just how incredibly shallow this well is. The forces involved are minuscule.
What does that mean practically?
It means two things, primarily. First, the antihydrogen atoms have to be ultra-cold. Typically colder than half a Kelvin, that's less than half a degree above absolute zero. If they're moving too fast, they'll just fly right out of the shallow magnetic trap.
Minuscule forces, super cold atoms.
Yeah.
Sounds delicate.
Extremely delicate. And second, to make the magnetic well deep enough to hold even these ultra-cold atoms, you need really strong magnetic fields with very specific shapes. That requires powerful superconducting magnets, which themselves need to be cooled with liquid helium down to about 4.2 Kelvin.
Wow. Okay, so you've got the charged particles buzzing around in their Penning trap, and you've got this separate concept, the magnetic well trap for neutral antihydrogen. How do you actually get the antihydrogen into that magnetic well? You can't just pour it in.
Yeah, that's the million-dollar question. And it's a major, major challenge. The problem is there's currently no efficient way to cool antihydrogen after it's formed. It's neutral. So the cooling tricks we use for charged particles don't work.
So you can't make it hot and then cool it down in the neutral trap.
Nope. It has to be born cold, essentially. Or at least cold enough to be trapped by that very shallow magnetic well the instant it's formed.
Right.
This means you have to create the antihydrogen directly inside the neutral trap volume. It's called in situ synthesis.
Create it right where you want to trap it. How?
This leads to these incredibly complex combined or nested trap designs. You basically have to build the Penning-Malmberg trap, where you hold and mix the antiprotons and positrons physically inside the magnetic structure of the Ioffe-Pritchard trap. The two traps are superimposed on each other.
But hang on, didn't you say the Penning trap needs a strong, uniform magnetic field, and the Ioffe-Pritchard trap relies on highly non-uniform, spatially varying fields? Isn't that a fundamental conflict? How can you have both at the same time in the same place?
It is a fundamental conflict. That's one of the biggest headaches. The inhomogeneous fields from the neutral trap's multipole magnet and mirror coils can leak into the Penning trap region and seriously mess with the delicate orbits of the charged particles, kicking them out before they can even form antihydrogen.
So how do they solve that?
Well, this is where some really clever engineering and physics comes in. The ALA-PHA collaboration, for example, made a breakthrough by using an octopole magnet for their radial confinement in the neutral trap.
And why is an octopole better?
Its magnetic field strength increases much more steeply as you move away from the central axis. It goes up like radius cubed, compared to a simpler quadrupole magnet where it increases linearly with radius r.
Okay,
So this means the octupole's field is significantly weaker right near the central axis, which is exactly where the charged antiproton and positron plasmas are being held and mixed in the nested Penning trap. It's less disruptive right where it matters most.
So it's a smarter magnet design that creates the neutral trap well, while minimizing the interference with the charged particle trap sitting inside it.
Precisely. This kind of optimization, finding ways to make these conflicting requirements coexist, was absolutely crucial for achieving the first trapping of neutral antihydrogen. It dramatically increased the number of antiatoms they could actually produce and keep hold of.
Incredible ingenuity. Okay, so these amazing complex machines, where is all this actually happening? Where's the action?
The undisputed world center for this kind of low-energy antimatter research is CERN, the European Organization for Nuclear Research near Geneva. They operate a unique facility specifically designed for this, built around something called the Antiproton Decelerator.
The Antiproton Decelerator, or AD. So how do they get the antiprotons to decelerate in the first place? Where do they come from?
Right, well, antimatter doesn't just lie around on Earth, so you have to make it. At CERN, they take ordinary protons, accelerate them to very high energy in one of their big accelerators, the proton synchrotron, and then they slam this proton beam into a block of metal, a target.
And that makes antiprotons.
These incredibly energetic collisions produce a whole zoo of secondary particles. Among them is a tiny, tiny fraction of antiprotons. But these antiprotons are wild. They're created with enormous energies and flying off in all directions. They're way too hot and unruly to be trapped directly.
So they need to be tamed, calmed down.
Exactly. And that's the job of the Antiproton Decelerator, the AD. It's a storage ring about 188 meters around. It captures these wild antiprotons, slows them down dramatically using electric fields, and cools them using techniques involving electron beams. It takes this chaotic spray and turns it into a usable, relatively low-energy beam that can then be sent to the various experiments.
And I heard there's an upgrade to the AD now, Elena.
Yes. ELENA, that stands for Extra Low Energy Antiproton Ring, is a crucial recent addition. It's a smaller ring, only 30 meters around, that sits after the AD. It takes the antiprotons from the AD and decelerates them even further, by about a factor of 50, down to just 0.1 MeV.
Why go even slower?
Because it makes it much easier for the experiment's Penning traps to capture the antiprotons. The slower they arrive, the less energy the traps have to dissipate. ELENA has been a game changer, increasing the number of antiprotons the experiments can actually trap by a factor of 10 to 100. It's made everything much more efficient.
Huge difference. Okay, let's talk about some of those experiments using this beam. ALPHA comes up a lot, the antihydrogen laser physics apparatus. What's their main focus?
ALPHA's primary goal is to perform really high-precision spectroscopic measurements on trapped antihydrogen atoms. They basically shine lasers on the trapped antiatoms and measure the frequencies of light they absorb or emit, corresponding to transitions between energy levels.
And compare that to regular hydrogen.
Exactly. They compare their measurements on antihydrogen directly to the incredibly precise measurements we have for ordinary hydrogen. According to CPT Symmetry, they should be identical. Any tiny difference would be a massive discovery, a direct violation of CPT. They also use their trapped antiatoms to study how antihydrogen interacts with gravity.
And they use that sophisticated combined trap setup we discussed. The Penning trap inside the Ioffe-Pritchard neutral trap?
Yes, that's their workhorse. A Penning-Malmberg trap nested inside an Ioffe-Pritchard trap that uses a superconducting octopole magnet for the radial confinement. This whole setup allows them to synthesize the antihydrogen right there in the trap in situ, and then hold on to the neutral antiatoms for long enough to do these precise measurements.
What are some of LPHA's big achievements? What stands out?
Oh, they had a really impressive track record of firsts. They were the first group ever to successfully trap neutral antihydrogen atoms back in 2010. That was huge. Then they managed to hold on to them for longer and longer times, eventually over 1,000 seconds.
Wow, over 16 minutes.
Yeah. Holding on to neutral antimatter for that long is incredible. They've also performed the first measurements of key spectroscopic lines in antihydrogen, like the 1s-2s transition and the hyperfine structure. They even demonstrated laser cooling of antihydrogen recently, which is another major step. And as we mentioned, they made that first direct observation in 2023, showing antihydrogen falls down due to gravity. They're real pioneers.
Okay, so LPHA is doing precision spectroscopy and check that antihydrogen falls down. But other experiments are specifically trying to weigh antimatter, right, to measure its gravitational acceleration precisely. Tell us about GVR and EGs.
Right. GBR and AGs have that as their primary mission. Measure the gravitational acceleration of antihydrogen, often called G-bar, as accurately as possible. They're directly testing Einstein's weak equivalence principle, which says gravity should affect all matter and antimatter in the same way, regardless of composition.
Is there any reason to think it might be different?
Well, general relativity predicts no difference, but it's never been directly tested with antimatter until recently. Finding any deviation, however small, would be absolutely revolutionary. It would mean general relativity is incomplete, or maybe there's a new fundamental force acting differently on matter and antimatter.
So how are GBR and AG trying to measure this G-bar? What are their approaches?
They take quite different tacks. GBAR, that's gravitational behavior of antihydrogen at rest, uses a really clever trick. First, they make an ion of antihydrogen, H-bar+, which is an antiproton with 2 positrons attached.
Why an ion?
Because it's charged. That means they can trap it easily in an ion trap and cool it down to incredibly low temperatures, microkelvin levels, using laser-cooled beryllium ions nearby for sympathetic cooling. Once it's almost perfectly still, they use a laser pulse to gently knock off the extra positron. Zap. Now you have a neutral antihydrogen atom that is essentially at rest.
Okay, an ultra-cold stationary antiatom. Then what?
Then they simply turn off the trap and measure the time it takes for the antiatom to fall under gravity over a known distance, about 20 centimeters. By measuring that freefall time very precisely, they can calculate G-bar, and GBR was actually the very first experiment to use the new, much slower beam from ELENA.
Very neat. And EGI, what's their method?
Aegis antihydrogen experiment. Gravity interferometry spectroscopy takes a different approach. They aim to create a pulsed beam of antihydrogen atoms moving horizontally. This beam is then passed through a device called a Moiré deflectometer.
A Moiré deflectometer.
Yeah, think of it like two fine gratings placed one after the other. As the antihydrogen atoms fall slightly under gravity while passing between the gratings, it creates a characteristic shadow pattern on a detector downstream. By measuring the tiny vertical shift in this pattern, they can determine how much the anti-atoms fell and thus deduce the effect of gravity.
Two very different ways to measure the same thing. Have they got results yet?
Both experiments have successfully produced antihydrogen, which is a huge step in itself. They are now working hard towards making those precision measurements of G-bar. It's incredibly challenging work.
Absolutely. Now, there's one more major player at the AD base, the baryon-antibaryon symmetry experiment. They're not looking at antihydrogen, are they?
No, BASE takes a different angle entirely. They focus directly on the building block, the antiproton itself. Their goal is to compare the fundamental properties of the proton and the antiproton with the absolute highest precision possible. Specifically, they measure their charge-to-mass ratios and their magnetic moments.
Another test of CPT symmetry.
Exactly. CDT symmetry predicts that the proton and antiproton should have exactly the same mass, and their charges and magnetic moments should be equal in magnitude, but opposite in sign. BASE is pushing the limits on how precisely we can verify that prediction.
How do they achieve such high precision? What's their technique?
They use a very sophisticated multi-penning trap system designed for measurements on single isolated particles. A key technique is to simultaneously trap a single antiproton in one trap chamber and a single negative hydrogen ion, H-, in a nearby parallel chamber within the same magnetic field.
Why the H- ion?
The H- ion, a proton with 2 electrons, has almost the same charge-to-mass ratio as an antiproton, but it's made of normal matter. By measuring both particles simultaneously or in rapid succession, they can cancel out many systematic errors, especially tiny fluctuations in the main magnetic field, allowing for incredibly precise comparisons.
And what have they found?
BASE has achieved the world's most precise measurement of the antiproton's magnetic moment. They found it to be consistent with the proton's magnetic moment, just with the opposite sign as expected, to an astonishing precision of parts per billion.
Parts per billion?
Yes. It's one of the most stringent tests of CPT symmetry ever performed in the baryon sector particles made of quarks, like protons and neutrons. So far, CPT holds up perfectly under their scrutiny.
That's amazing precision. But I also heard BASE did something else quite remarkable recently. Something about moving antimatter.
Ah, yes. That was the BASE STEP project. This was truly groundbreaking. They designed and built a transportable Penning trap system. It weighs about 2.5 tons, includes its own superconducting magnet, cryogenics, detectors, the works. And they successfully trapped antiprotons in it at the AD facility, sealed it up, put the whole thing on a truck, drove it across the CERN campus to a different experimental hall, plugged it back in, and confirmed the antiprotons were still safely trapped inside.
They put antimatter on a truck. Seriously. That sounds risky.
It sounds risky, but it was done with extreme care and sophisticated engineering, including a special airlock system and non-destructive detectors to monitor the antiprotons. It was a stunning demonstration.
What's the significance of being able to transport antimatter like that?
It's potentially huge. It could represent a paradigm shift. Right now, all of these experiments have to be physically located right next to the AD, the only source of low-energy antiprotons. If you can safely transport trapped antiprotons, even in these small quantities, it opens up the possibility of doing experiments elsewhere, perhaps in labs with specialized equipment or maybe even smaller university labs. It could democratize access to antimatter research, decoupling it from the single big production facility.
A client-server model for antimatter. CERN makes it, BASE delivers it.
Something like that could be the long-term vision, yes. It could fundamentally change how this research is done.
Looking at all these experiments, alpha, G-bar, Aegis, BASE,
Yeah.
it really seems like a well-thought-out strategy at CERN. It's not just random shots in the dark.
Absolutely. It's a highly complementary, multi-pronged attack on fundamental questions. Each experiment uses different techniques to probe different aspects of antimatter and the underlying symmetries. Ioffe-Pritchard looks at CPT via atomic structure, GBR and Aegis tests gravity's effect, BASE tests CPT via intrinsic particle properties. This diversity maximizes the chances of a discovery or allows them to set very strong limits if no deviations are found. It's a smart way to maximize the scientific return from the unique AD and ELENA facilities.
So we've heard about these incredible scientific achievements, these super complex traps. What does this all mean for the big picture? Is antimatter going to power our starships like in Star Trek? Is it going to solve the energy crisis? Where does this lead practically?
Right, that's the inevitable question, especially given how much antimatter features in science fiction. And it's important to be realistic here. While the laboratory's successes in trapping and manipulating tiny amounts of antimatter are truly spectacular scientific feats, there is a vast gulf separating these experiments from any kind of large-scale application. A chasm, really. The path forward for applications like propulsion or energy is currently blocked by absolutely formidable hurdles. We're talking about fundamental technological and economic barriers related to making it, storing it, and handling it in bulk.
Okay, let's talk about production first. You mentioned it's inefficient. How bad is it?
It's monumentally inefficient. Remember Elena boosting trapping efficiency by 10 to 100 times? Even with that, at CERN, maybe only one antihydrogen atom is successfully trapped for every 10,000 or so that are produced initially.
1 in 10,000. Wow.
And that inefficiency translates directly into astronomical costs, both in energy and money. To produce just 1 gram of antimatter using current accelerator methods, estimates suggest it would require something like 25 million billion kilowatt hours of energy.
Wait, 25 million billion kilowatt hours. How much is that?
That's roughly equivalent to the total annual energy consumption of the entire planet for 1 gram.
The whole planet's energy use.
Yeah.
For 1 gram. That's mind-boggling.
Another way to look at it. For every unit of energy you could theoretically get out by annihilating antimatter, you'd have had to put something like 10 billion units of energy in to create it in the first place.
10 billion to 1. Okay, that definitely puts a damper on the antimatter as a fuel source idea.
It makes it nonsensical for energy generation, yes. And the financial cost. Estimates float around, but a commonly cited figure is something like $62.5 trillion per gram.
Trillion with a T.
Trillion with a T. So, given these staggering costs and inefficiencies, current production is limited to truly microscopic quantities. The AD at CERN produces maybe about 10 nanograms. That's billionths of a gram of antiprotons per year. The total amount of antimatter artificially produced by humans in all of history is probably only a few nanograms. Its utility right now is purely for these fundamental science experiments using tiny numbers of particles.
Okay, so production is a killer problem. Even if you could make more, what about storing it? Can we store large amounts for long times?
Storage is the other side of the coin, and it presents its own daunting challenges. Yes, experiments have achieved amazing milestones, like holding that single antiproton for 57 days or thousands of antihydrogen atoms for over 16 minutes. But these are under absolutely pristine, carefully controlled laboratory conditions with minuscule quantities.
What happens when you try to scale up? More quantity, longer duration.
You run into major bottlenecks. First, system integrity is incredibly fragile. These traps rely on the flawless, continuous operation of multiple complex systems, the ultra-high vacuum, the cryogenics keeping everything super cold, stable power for the magnets and electric fields. Any failure, a power flicker, a tiny vacuum leak, means immediate, total, catastrophic loss of whatever antimatter you were holding.
No room for error.
None. And then there's the quantity limit itself. Current traps hold thousands, maybe millions of antiatoms. That's a huge number for experiments, but it's utterly insignificant compared to the grams or kilograms, which is like 10 to the power of 23 atoms you'd need for any practical application.
And just trying to cram more in causes problems.
Yeah, as the density of the trapped antimatter increases, you start getting issues like self-heating from annihilations, with the few residual gas molecules still bouncing around in even the best vacuum. And interactions within the antimatter cloud itself could become problematic. Scaling up isn't straightforward at all.
So even with that amazing base step project showing you can transport a tiny amount, we're still fundamentally limited to these incredibly small, incredibly fragile samples kept under extreme conditions.
Exactly. Base step was a fantastic proof of principle. It showed safe transport is possible. And maybe it leads to miniaturization, perhaps using permanent magnets instead of big superconductors, which could help democratize research access, as we discussed. But doesn't solve the underlying problems of producing large quantities or storing them stably in bulk.
Okay, so let's just state it clearly then. Based on everything we know now, large-scale applications, antimatter for energy generation, antimatter for spacecraft propulsion, these are just not feasible.
Unequivocally no. Not with current technology. And not with any foreseeable technology based on our current understanding. Using antimatter for terrestrial power makes zero sense because of the horrific energy input costs. Pure annihilation rockets, like in Star Trek. Firmly science fiction. Even more modest sci-fi concepts, like using tiny amounts of antimatter to catalyze nuclear fusion reactions, are still way beyond anything we can currently achieve in terms of production and storage.
And I guess we should also mention the safety implications if you did somehow have a macroscopic amount.
Oh, absolutely. A containment failure in a hypothetical system holding, say, grams of antimatter wouldn't be like a nuclear reactor meltdown where the reaction might fizzle out. It would be an instantaneous, catastrophic explosion. The entire stored mass would convert to high-energy radiation essentially all at once. It's hard to even comprehend the devastation.
Right, so if it's not for power, not for propulsion, not anytime soon anyway,
Right.
then why? Why this immense effort, this incredible ingenuity, these fiendishly complex machines? What is the true purpose of all this groundbreaking work in antimatter containment?
That's the crucial question, and the answer is fundamental discovery. The immense effort, the decades of work, the huge investment. It's not driven by hopes of near-term applications. It's driven by the quest to forge a unique key, a tool capable of unlocking some of the deepest, most persistent mysteries about the universe we live in.
Mysteries like what?
By isolating these antiatoms, manipulating them, studying them with incredible precision, scientists are performing exquisitely sensitive tests of the universe's fundamental symmetries. These symmetries underpin our entire understanding of physics. These tests probe the very nature of space, time, matter, energy, gravity, and they seek answers to really profound questions. Questions like, why is the universe the way it is? And maybe the biggest one of all, why does a universe made of matter even exist?
Okay, let's unpack those mysteries. You mentioned testing CPT symmetry. What exactly is that again, and why is testing it so vital?
Right, CPT symmetry. It's really a cornerstone of our current best theory of particle physics, the Standard Model. It basically states that the laws of physics should look exactly the same if you simultaneously do three things. Swap all particles with their antiparticles, charge conjugation, C, look at everything in a mirror, parity inversion, P, and run time backwards, time reversal, T.
C, P, and T together.
Yes. A direct consequence of this combined CPT symmetry is that a particle and its antiparticle must have certain identical properties, like the same mass, the same lifetime if they're unstable, and other properties that are equal but opposite, like electric charge and magnetic moment. Verifying this prediction with the absolute highest precision possible is a primary goal of antimatter research.
And experiments like BASE and Ioffe-Pritchard are the ones doing that verification.
Exactly. BASE, by comparing the proton and antiproton's magnetic moments and charge-to-mass ratios down to parts per billion, puts incredibly tight constraints on any possible CPT violation in the baryon sector. ALPHA does it by comparing the energy levels, the spectroscopic fingerprint of antihydrogen, to ordinary hydrogen. Any difference they found would be a direct signal that CPT symmetry is broken.
The stakes seem enormous if they did find a difference.
Oh, they are absolutely huge. Finding a confirmed violation of CPT symmetry would shatter one of the fundamental pillars of the Standard Model. It would be undeniable proof of new physics beyond our current understanding. It could provide the first real experimental clues pointing towards more advanced, more fundamental theories, maybe things like string theory or quantum gravity. It would change everything.
Antimatter fall down.
Yes. This is all about testing another core principle, this time from Einstein's theory of general relativity, the weak equivalence principle.
The weak equivalence principle.
It basically states that the way gravity affects an object is completely independent of what that object is made of. A kilogram of feathers should fall at the same rate as a kilogram of lead, assuming no air resistance. And according to this principle, a kilogram of antimatter should fall at exactly the same rate as a kilogram of matter.
So gravity shouldn't care if it's matter or antimatter.
That's the prediction. But while it was long assumed to be true, it had never actually been directly tested with antimatter until very recently. It's a fundamental assumption we needed to check experimentally.
And ALPHA did that check in 2023, confirming antihydrogen falls down, ruling out any simple anti-gravity idea.
Correct. That was a landmark result. Now the next step, which is what experiments like GBR and EG are designed for, is to measure how fast it falls. To determine the gravitational acceleration, G bar, for antihydrogen with high precision, and see if it's exactly the same as G for normal matter.
And if they find it's even slightly different.
Again, revolutionary. Any confirmed deviation, no matter how small, would mean general relativity is incomplete. or that there's some new, previously unknown fundamental force in the universe that interacts differently with matter and antimatter. It would open up a whole new landscape in physics.
Wow, okay, CPT and gravity. Finally, you mentioned perhaps the biggest mystery of all, the baryon asymmetry. Why is the universe made of matter?
Ah, yes, the baryon asymmetry. This is arguably one of the greatest unsolved puzzles in all of science. According to our standard model of cosmology, the Big Bang should have produced matter and antimatter in almost perfectly equal amounts.
Equal amounts.
Yeah.
So what should have happened?
Well, as the early universe cooled, all that matter and antimatter should have found each other and annihilated, converting everything back into pure energy, into light. The universe should be empty of matter, just filled with radiation.
But it's clearly not. We're here. Galaxies, stars, planets exist.
Exactly. The fact that we exist, the fact that all the structures we see in the universe are made of matter, implies that somehow, in the very early moments, a tiny imbalance occurred. For roughly every billion pairs of matter and antimatter particles that annihilated, one extra matter particle was somehow left over. Just 1 in a billion excess of matter survived. And that tiny remnant is what everything we see today is made of. Why? How did that happen? We don't have a complete answer.
And how do these antimatter containment experiments help solve that profound puzzle?
They are all searching for the crucial clue, the missing piece that could explain that primordial imbalance. The Russian physicist Andrei Sakharov outlined conditions needed for this asymmetry to arise back in the 60s, and one key condition involves differences in how matter and antimatter interact or decay, something called CP violation. We've observed some CP violation, but not nearly enough to explain the huge matter excess we see.
So we need something more.
We need something more. Maybe CPT symmetry itself is slightly violated. If L Fichet or base were to find such a violation, that would imply a fundamental difference in the rules governing matter and antimatter, providing a potential mechanism for that early universe preference for matter.
Or maybe gravity is involved.
Or maybe gravity plays a role differently. If GBR or EJs were to find that antimatter falls slightly differently than matter, that would point towards a new force or a modification of gravity that could have acted to separate matter and antimatter in the early universe, preventing their complete annihilation.
So essentially, all these incredibly sophisticated technologies, all this effort poured into trapping antimatter. It's all about searching for a tiny crack, a slight imperfection in that perfect mirror symmetry between matter and antimatter.
Precisely. They're looking for any hint of asymmetry. Because finding that asymmetry, that crack in the mirror, could finally explain why the universe made the choice it did, why it chose matter over antimatter. And ultimately, that explains why we are here asking these questions in the first place.
What an incredible journey. We've gone from the seemingly impossible problem of just holding on to antimatter to understanding the basic annihilation imperative, the cleverness of Penning traps for charged particles, the even greater challenge of trapping neutral antihydrogen with magnetic fields in Ioffe-Pritchard traps, and seeing how these come together in the amazing combined traps at CERN.
Yeah, the ingenuity involved is just breathtaking, from the fundamental physics principles to the engineering marvels required to make them work.
And we've seen that while the sci-fi dreams of antimatter power and propulsion are, well, still firmly science fiction due to the immense challenges of production and storage.
Definitely still science fiction for now.
The true and current value of this work is profound. It's an absolutely irreplaceable tool for tackling some of the deepest questions in fundamental physics, testing CPT symmetry, probing gravity's effect on antimatter, and searching for clues about why our universe is made of matter.
Absolutely. The ability to contain and manipulate antimatter, even these tiny amounts, gives us a unique window into the fundamental laws of nature, the precision they achieve, the collaborations involved. It's really science at its most challenging and potentially most rewarding.
It really makes you think, doesn't it?
Yeah.
If all these painstaking efforts, trapping this elusive stuff, studying it particle by particle, if it's ultimately about understanding why we exist, why we live in a universe made of matter, what does that whole endeavor tell us about us? About humanity's enduring quest to understand the fundamental truths of the cosmos, even when the answers might force us to rethink everything we thought we knew.
That's definitely something to ponder. The drive to know, even when it's incredibly difficult and the answers might be deeply strange.